So starting with P block, what you can say elements, we will see that is group 16 elements, rather I should say. In the group 16 elements, we have got the oxygen family, the group 16. Now group 16 also consists of not only oxygen, it also consists of sulfur, selenium, tellurium, polonium, etc. The first four elements of the group, that is oxygen, sulfur, selenium and tellurium, are chalcogens, we can say that. Why it is called chalcogens? Because chalcogens meaning ore forming elements. Large number of metal ores found in the earth's crust are oxides and sulfides. For that reason they are called as chalcogens, ore forming elements. Oxygen is the most abundant element, sulfur occurs less abundantly. Got it? Out of that. Now, what you find is that is polonium has come from the what you can say, it is a radioactive element and is derived from the name that is from the Poland, the home country of Madame Curie, Marie Curie, we can say that, who discovered the element in 1897 around, we can say that. So now electronic configuration, if you see, they have 6 electrons in their valence shell, 2 in the S and 4 in the P subshell. 2 in the S subshell and 4 in the P subshell, that is NS2NP4, we can say that. The outermost configuration I am saying you, because always we are generally concerned with the outermost configuration only. Among the 4 electrons present in the NP subshell, 2 are paired while the other 2 are unpaired. That's very important to remember it. Among the 4 electrons present in the NP subshell, 2 are paired while the other 2 are unpaired. You can write it and see this particular thing. You can take any electronic and any particular element and you can write it and see. So oxygen, the first member of the group 16, is a gas, while all other elements of the groups are solids at ordinary temperature. This is due to the fact that oxygen exists as a diatomic molecule, while other elements of the group form complex molecules, example S8. Got it? S8. Now you can see it on the screen. Oxygen forms p-pi double bonds, but other elements do not. However, sulfur and other elements of this group possess d orbitals. Oxygen only possesses p orbitals. So due to this reason, it forms p-pi d-pi multiple bonds. Got it? Due to this reason, it possesses p-pi d-pi. Oxygen possesses p-pi multiple bonds because it has, oxygen has got p subshell. It has got no d subshell. It has got no vacant d subshell, or no d subshell is there, we can say that. The overlapping between two oxygen atoms leads to the formation of O double bond O bond. Intermolecular forces between oxygen molecules are only weak van der Waals forces. This is why oxygen exists as a gas at ordinary temperature. I told you the reason why it is a gas. The higher elements of the group like sulfur, selenium, etc. are unable to form p-pi bonds with a large atomic size. Therefore, it forms what? What I said you, it forms p-pi d-pi multiple bonds. P-pi d-pi multiple bonds, we can say that. So therefore these elements do not occur as diatomic molecules. Sulfur and other elements of this group linked their atoms by single bond to form a polyatomic complex molecule. Polyatomic complex molecule it forms, we can say that. Like sulfur has got 8 atoms joined together through single bonds and it forms a puckered ring like structure. So I think I have that particular diagram of the puckered ring like. I can show it to you, the puckered ring like structure. No, I don't have. I will show you in some other AV. I can show you to you in other AV, we can say that. That is the puckered ring like, that's the 8 atoms are joined together. Got it? And it forms a strong bond and it forms a crown structure. Puckered ring is nothing but a crown like structure, like the king is having a crown upon its head, similar, that sort of structure, we can say that. That is a crown structure, we can say. So it is due to the polyatomic molecules are held together by strong van der Waals forces, we can say that. Because of the stronger, now you can see it on the screen, because of the stronger SS bonds as compared to OO bonds, sulfur has a strong tendency for catenation than oxygen. It undergoes large number of catenation, we can say that. It can combine with itself and also with other atoms, we can say that. Clear? The atomic radii of group 16 elements are smaller than those of the group 15 elements. Of course we know this. and when you move across the period, the atomic size decreases, and when you come down the group, atomic size increases due to the increase in number of shells. The density of the group 16 elements increases on moving down the group. Why? Because the same thing, the atomic size is decreasing. So more number of molecules is being added, so the mass is increasing, so density is also increasing, we can say that. So that is when one moves down the group, the atomic size increases. This increases the magnitude of van der Waals forces of attraction acting between the molecules, and consequently the lattice and becomes more compact, hence density increases on moving down the group. Got it? Similarly, the melting and boiling points of group 16 elements increases regularly on going down the group. However, the melting and boiling points of polonium are smaller than those of selenium. The polonium is smaller, the melting and boiling points, so because it's a metal, mind it, it's a radioactive substance, so are smaller than those of selenium. The increase in melting point, the reason I'm giving you now, the increase in melting and boiling points on moving down the group is due to an increase in the magnitude of van der Waals forces, because atomic size is increasing, so van der Waals force is also increasing. The comparatively lesser melting and boiling points of polonium as compared to that of selenium, listen carefully, is due to the inert pair effect, which is maximum in polonium due to its maximum nuclear charge. It is maximum in polonium due to its maximum nuclear charge, we can say that. Got it? Now next is, so that is, you can see it here that I have already said you that oxygen, the first member of the group, shows only a little tendency to undergo catenation, we can say that. Clear? So it has got a little tendency, but sulfur shows a greater tendency towards catenation and link up several atoms in chains to form what you can say, the polysulfides, sulfanes, polysulfuric acid, and so on, we can say that. Got it? Now that is, if you see the allotropy, then all the elements of this group shows allotropy. For example, oxygen exists in two non-metallic forms like dioxygen and ozone. Sulfur has several allotropic forms. Selenium has got 8 allotropic forms. Now if you see the allotropic form of sulfur, then we have got homocyclic species containing 6 to 20 sulfur atoms. Among these species, the most common and thermodynamically most stable form is the orthorhombic S8 molecule. I said, 6 to 20 sulfur atoms are joined, but the one which is thermodynamically stable is the orthorhombic sulfur S8 molecule. Now catena Sn sulfur, N means any number of molecules ranging from 2 to 5, the value. These are the chain polymers, unstable small Sn molecules, we can say that. Like oxygen molecules, S2 molecules are also paramagnetic. It's very important, you can note it down. Like oxygen molecules, S2 molecules are also paramagnetic. I said you already, you can see selenium exists, has 8 allotropic forms. Out of that, that is, we are having alpha, beta, gamma, red monoclinic forms containing Se, 8 rings, we can say that. Clear? The stable form is the gray hexagonal monoclinic form, which consists of infinite spiral chains present in it. In case of selenium, I'm talking to you. Now tellurium and polonium also shows allotropy. Tellurium exists in 2 allotropic modifications, metallic and non-metallic. Polonium has 2 allotropic modifications, namely alpha form and beta form, both of which are metallic in nature. You can note it down, both of which are metallic in nature. Polonium has 2 allotropic forms, namely alpha form and the beta form, so to say. So now oxygen, the first element you can see on the screen of this group, has high electronegativity. Oxygen having the first element, the elements of the group 16 itself has got higher value of electronegativity as compared to those of group 15 elements, we know that. So oxygen is the second most electronegative element. You can note it, the oxygen is the second most electronegative element, the first being fluorine. In terms of electronegativity, we can say that electronegativity value decreases on moving down the group. On moving down the group, what happens is that the size of the atom increases and consequently effective nuclear charge decreases. This is why electronegativity decreases from oxygen to polonium. Now what you see is that in terms of oxidation state, In addition, oxygen shows an oxidation state of -1 in peroxides. In the screen you can see, such as H2O2, -1, the oxidation state of oxygen in peroxide is, -0.5 in superoxide such as KO2, and 0 in oxygen and O3, and +1 in O2F2 and +2 in OF2. Now these things you have studied last year in redox reaction chapter, we can say that. So all the elements of group 16 exhibit an oxidation state. Correct. So the reason is that being strongly electronegative, these elements prefer to gain 2 electrons to attain noble gas configuration, and thus it exhibits an oxidation state of -2. Apart from that, as I said you, we have got -1, -0.5, +1, 0, we are there. It is there, but generally the elements of group 16 exhibits an oxidation state of -2. I told you the reason, because being strongly electronegative, these elements prefer to gain 2 electrons because it has got 6 electrons in the outermost shell. So it prefers to gain 2 electrons to attain the nearest noble gas configuration, so to say. Sulfur and other heavier elements of the group also shows oxidation state of +4 and +6. The +4 and +6 states are more stable, remember it. The +4 state is exhibited when these elements excite their Np electrons to Nd subshells in the first excited state, and in the what you can say +6 state, it is exhibited when Ns electron are excited to Nd orbitals. Again I repeat, the +4 state is exhibited when these elements excite their Np electrons to Nd orbitals, vacant orbitals, in the first excited state. And in the second excited state, that is a +6, where Ns electron are excited to Nd orbitals. Alright, clear? So in this way it shows an oxidation state of also +4 and +6. The oxidation state of +4 and +6 are quite common for sulfur, selenium and tellurium. For the last member of the group, that is polonium, the +4 oxidation state is more stable than the +6. Already I said you, due to inert pair effect, so to say, due to inert pair effect. Fine. Now coming to the screen, the electronegativity decreases as we move down the group. The tendency of these elements to show -2 oxidation state also decreases. That I have said you already. All the hydrides of the elements of group 16 are volatile. Yeah, they are volatile in nature. The volatile, however, first increases from water to H2S and then decreases from H2SE to H2TE, we can say that. Clear? So the abnormality, high boiling point of H2O is due to strong intermolecular hydrogen bond that we have studied in lower classes. That water, if you see the that is a boiling point, if I consider, then water is having higher boiling point, then H2S we can say that. So white water is having the higher boiling point due to H2S, because we know that due to the presence of intermolecular hydrogen bonding in water. So there is strong intermolecular hydrogen bonding. Got it? So if you see, that is the hydrides of group 16, what you can say, forms hydrides of the type H2M. Here M means, capital M means your oxygen, sulfur, tellurium or polonium, that is group 16 elements. As a result, it forms H2O, H2S and H2C, H2T and H2PO. Okay, so oxygen forms another important hydride, that is hydrogen peroxide, H2O2. We can say that because oxygen, you have read it, it has got several oxidation state. Got it? In -1 oxidation state, it shows a peroxide. You can see on the screen, it is there. All these hydrides have angular structure. Note it, all these hydrides, they have got angular structure and are found by sp3 hybridization of the central group 16 atom in the ground state. Got it? Clear? Water, that is the hydride of oxygen, is a colorless and odorless liquid, while the hydrides of all other elements of the groups are colorless, poisonous and unpleasant gases with unpleasant odor, we can say that. Got it? Water, the hydride of oxygen, is a colorless, odorless liquid, while the hydrides of all other elements of the group are colorless, they are poisonous with gases with unpleasant odor. The volatility of these hydrides first increase from H2O to H2S and then decreases. Got it? H2O to H2S first increases, then it decreases. Then H2SE, H2TE decreases. We can say that. Clear? Fine. So that is H2S is more volatile of all the hydrides of the group. We can say that. Alright, H2S, and H2O is having a higher boiling point. Alright, due to the presence of intermolecular hydrogen bonding. In terms of that only, if you see the thermal stability of hydrides of group 16 elements decrease in the order. The thermal stability of the group 16 elements decreases in the order H2O is greater than H2S is greater than H2SE is greater than H2TE. Alright, the thermal stability. That is, in going from H2O to H2TE, the size of the central atom increases and therefore its tendency to form stable MH bond. Here M again I say, it represents not metal, it represents the group 16 elements, decreases. Alright, that is, when you are coming down the group, its tendency to form stable MH bond decreases. Alright, due to this reason, the thermal stability of the group 16 is decreasing in the order from H2O to H2TE. The hydrides of group 16 elements are weakly acidic in nature and behaves as weak diprotic acids. Diprotic acids are acidic in nature, weak acidic in nature. H2S plus H2O, it will give you what? H3O plus HS minus. Again, HS minus reacts with water molecule to form H3O plus and H2 minus. So how many H plus ions you are getting? In how many steps you are getting it? You are getting 2 steps. So hence it is called as a diprotic acids. Alright, it is known as diprotic acids. And acidic strength increases from H2O to H2TE. The acidic strength increases. Water is the least acidic of all the hydrides of the group, of this particular group, we can say that. Water is the least acidic. And if you see the reducing character, then except water, all other hydrides of the elements of group 16 act as a reducing agent. The reducing power of these hydrides increases from H2S to H2TE. H2O is a very stable. Why it is that it increases from H2S to H2TE? The reason is H2O is very stable. It does not act as a reducing agent. Just now I said you. The other hydrides, what you can say, are relatively less stable and act as a reducing agent. Alright, again I repeat that H2O is very stable. It does not act as a reducing agent, while the other hydrides are relatively less stable and act as a reducing agent. We can say that. So this is about your hydrides. You came to know that they are acidic, they are thermally stable, they have got reducing character, they have volatility. Got it? Their physical state is that they are volatile in nature, and which is more volatile, which is less volatile. I've said you everything I've discussed with you. Alright, so you can see it here, it is on the screen also, it is there, it is written. Now but the hydrides I've discussed with you. Now next is if you see the ionization energy of the group 16 elements are quite high, and it is very difficult to remove electron from their valence shells of their atoms. The ionization energy decreases on moving down the group. Alright, now why it is high and why it decreases down the group? The reason is that the high ionization energy of group 16 elements are due to their small size and high effective nuclear charge, which is experienced by their valence electrons. Alright, therefore it requires a substantial amount of energy to remove electrons from the valence shell. See, atomic size is small, nuclear charge is bigger, so definitely you require a large amount of energy to remove the electrons from their valence shells, from the outermost shells. Due to this high ionization energy, these elements usually do not form cations. They do not form cations, they generally form what? Anions, we can say that. Clear? So coming to electron gain enthalpy also, the elements of group 16 have high values of electron gain enthalpy. The electron gain enthalpy of oxygen is less negative than that of sulfur. Note it. The electron gain enthalpy of oxygen is less negative than that of sulfur. Electron gain enthalpy value decreases on moving down the group from sulfur to polonium. Alright, from sulfur to polonium, if you come, then the electron gain enthalpy value decreases. We can say that. Alright, now that is, I just now said you about the acidic character. You come to the screen, you look at the screen, you can see that SF6 is a colorless, odorless and non-toxic gas at room temperature. It is thermally stable and chemically inert, we can say that. Its chemical inertness is due to the reason that 6 fluorine atoms protect the sulfur atom from attack by the reagents to such an extent that even thermodynamically most favorable reactions like hydrolysis do not occur. The fluorine atoms is there and it protects the sulfur atom. The fluorine atom is surrounding the sulfur atom. So sulfur atom does not come under the attack of hydrolysis also, means it no hydrolysis takes place. Hydrolysis replacement by OH group, we can say that also does not take place because fluorine is so stable, so strong, we can say that. So however, as the size of the central atom increases, steric hindrance decreases and hence hydrolysis becomes easy. Alright, means if you come down the group from sulfur, selenium, tellurium, polonium, if you see, then as the size will increase, so definitely the fluorine atom will no more be able to hold or protect this the central atom. Alright, due to what you can say steric hindrance, which decreases and hence hydrolysis becomes easier. Alright, but in case of SF6 it is not easier, I said you, because the fluorine atom protects the sulfur atom. So for that reason SF6 also, it's quite chemically inert and it does not go on hydrolysis under ordinary conditions, so to say, we can say that. So this is a little bit about your what you can say the properties or the characteristics of group 16 elements, so to say.